Hey everyone, and welcome! Today, we are diving deep into the heart of the periodic table, the D and F block elements. Now, these aren't just random letters and numbers on a chart. Oh no, they are the elements that literally color our world and build our modern technology from the ground up. I mean, just think about it for a second. The vibrant colors in stained glass, the incredible strength of steel in our skyscrapers, or even the invisible pull of a powerful magnet. All of that amazing stuff, it all traces back to the unique way the electrons are arranged deep inside these very atoms.
So here's our game plan for this explainer. First, we're going to map out our territory, what we're calling the middle kingdom of the periodic table. Then we'll crack open the secret rulebook that these elements follow. After that, we'll see how those rules create a whole spectrum of superpowers. We'll investigate a really weird phenomenon called the Lanthanoid squeeze. And finally, we'll see how these elements are absolutely essential for building the world we live in today.
All right, first things first. Before we get into the wild stuff, let's get our bearings. Where exactly on the periodic table are we even talking about? Okay, so you see that big, wide central block of the periodic table, groups 3 all the way through 12? Those are the D block elements, what we call the transition metals. And then you've got that separate little 2-row panel at the very bottom, right? That's the F block. That's home to the inner transition metals. But it's not just about where they live on the map. The official scientific definition is way more specific. The powers that be in chemistry say that a true transition metal has to have a partially filled D subshell. And this can be either when it's a neutral atom or when it's become an ion. This one little rule, it's the key to everything. And right away, that definition throws us a classic chemistry curveball. Take a look at zinc, all the way over in group 12. I mean, it's in the D block, right? It's in the neighborhood, but does it actually follow the rule? Is it really a transition metal? So let's break this down. On the left, we've got scandium. In its neutral state, it's got one electron in its D subshell. It's incomplete, so check. It's in the club. Now look at zinc. As a neutral atom, its D subshell is totally full, 10 out of 10 electrons. And even in its most common ion form, that D subshell is still full, since it never has an incomplete D subshell. Nope, sorry zinc, you're not technically a transition metal. All right, now that we know who gets in the door, let's take a peek at the secret rulebook they all follow. Because all the weird, cool, and wonderful things these elements do, it all comes down to their electron configurations. So this is the general formula for how their electrons fill up. You've got electrons going into the outermost s orbital and the d orbital of the shell just below it. But here is the absolute key to everything. The energy difference between those two orbitals is tiny. It's minuscule. And that closeness creates this incredible flexibility, letting electrons jump back and forth. That's the source of all the magic. And because those energy levels are so tight, you get some really famous rule breakers. You'd expect chromium to have 4 d electrons, right? But instead, one of its s electrons jumps ship and moves into the d orbital. Why? Because having a half-filled d subshell with 1 electron in each slot is just extra stable. It's a lower energy state. Copper does the exact same thing to get a completely full and super stable 3d10 configuration. Okay, so they have weird electron rules. Big deal, right? Who cares? Well, you do, because these quirky rules are what give rise to an entire spectrum of incredible, useful superpowers. Let's check them out. Just look at manganese. Because it can lose electrons from both its s and d orbitals, it's a total chameleon. It can have a charge or oxidation state of +2, all the way up to a whopping +7. This chemical flexibility is a defining feature of the transition metals, and it lets them do all sorts of amazing chemistry. And what's maybe the most beautiful consequence of this versatility? The incredible colors. The ability to have all these different oxidation states means these elements can absorb very specific colors of light, and what we see is the stunning, vibrant color that's left over. And you can see here, the color is directly tied to the number of d electrons. A titanium ion with just 1 d electron, it looks purple in water. Vanadium with 2 is green, and that familiar blue color of copper solutions, that comes from an ion with 9 d electrons. It's like a chemical paint palette. All right, superpower number 2, magnetism, specifically something called paramagnetism. This property just pops up anytime you have electrons that aren't paired up in an orbital. And since transition metals are famous for having lots of unpaired d electrons, many of them are paramagnetic, which just means they're weakly pulled in by a magnetic field. And this chart lays it all out, plain and simple.
The magnetic strength is directly tied to how many unpaired electrons you have. Titanium with 1 unpaired electron, a little magnetic, but manganese with 5 unpaired electrons, way more magnetic. It's a pretty straightforward rule. The more unpaired electrons, the stronger the pull.
Okay, now it's time to shift our focus to that mysterious bottom block, the F block elements, because they introduce a really strange, really powerful effect on the rest of the table, a genuine periodic table plot twist. So we all learn this basic rule, right? As you go down a column in the periodic table, atoms get bigger. And look, it works for the first 2 rows of the D block. The 4D series is bigger than the 3D. But then, look at the 3rd row, the 5D series. They're basically the same size as the row above them. What is going on here? That should not happen. Well, the answer to this puzzle has a name. It's called the Lanthanoid contraction. And it refers to this weirdly steady shrinking of atoms that happens as you move across that first row of the F block, the row that's slotted in right before those 5D metals begin. Here's the deal. The electrons that are filling up those 4F orbitals, they are just terrible at their job. Their one job is to shield the outer electrons from the pull of the positively charged nucleus. Because they do such a poor job, the nucleus can reach out and yank those outer electrons in much, much tighter than you'd expect. This pull shrinks the atom, and this shrinking effect added up over all 14 lanthanoid elements perfectly cancels out the size increase you'd normally get. That's the squeeze. So we've gone through the rules, the weird exceptions, the colors, the magnetism, and even that bizarre atomic squeeze. But let's pull the camera back and talk about why any of this matters. Why are these elements so fundamentally important? Well, their applications are literally everywhere. The D block gives us super strong alloys for building and incredible catalysts that make modern industry possible. There also are precious metals, gold, silver, platinum, that have shaped human economies for thousands of years. And don't forget the F block. Uranium fuels our nuclear power plants, and elements like neodymium are what make the super strong, lightweight magnets in your phone and in electric cars possible. And as this quote says so perfectly, you can basically trace the history of human civilization through our ability to master these elements. I mean, we name entire eras after them. The Bronze Age, the Iron Age, their unique properties have always been at the center of our progress. It's really incredible when you stop and think about it. These subtle, simple rules that just govern how electrons fill up 1 or 2 types of orbitals, they give rise to this immense diversity of properties that literally shape our entire world. It just makes you wonder, what other elegant and powerful rules of nature are hiding out there, right in plain sight, just waiting for us to figure them out? Thanks for joining me.